So it was more valuable. This same spectrum was now more valuable to mobile phones than it was for broadcasters. So the goal of this was to first run a reverse auction to the mobile broadband providers. And they define this class of auctions that I'm going to be defining formally. And our goal throughout this talk is to analyze but also tries to convince them to tell us what this value is, that they don't have incentive to lie. And to give you a concrete example that was kind of abstract, let's make it a bit more specific. Single-minded bidders is one example that many people have studied in the past, where a provider in this case owns a set of indivisible items, a set of things like the spectrum frequencies, say. And the buyers are single-minded in the sense that each buyer wants a specific subset of these items. Right? So this is a kind of combinatorial auction where each buyer needs a specific bundle of these items, and her value for these items is what the VI is. So essentially saying, I have a value. If I get this set of items, my value is VI. If I get anything less than that, my value is 0. So I value nothing other than that subset. So you can think of it as, let's say you have these 4 items over here, and you have a bidder saying, I want items A and B. So you can think of this as an edge. We're going to represent this as an edge in this talk. So you have this bidder over here who says, you know what, I want items A and B, and my value for it is 4. You can have another one who says, I want B and D, and my value is 1. A third one who says, I want A, C, and D, and you can think of it as a hyperedge in this graph, and my value is 6. And what I mentioned is, in this example, just going back to the definition I mentioned before, our goal is going to be to find what subset can we serve, give them what they want, aiming to maximize the sum of their values, the social welfare. So that's what we mean by efficiency. We want to choose the subset of these bidders that we serve to maximize some of the values. So if you think about it here, the best solution in this example would be to just serve that last guy because his value is 6, and therefore that's the best we could ever hope for. But in general, as you can imagine, this is a hard problem. It's an NP-hard problem. Another example would be a knapsack auction, where you have a knapsack constraint. Think of a plane. Right? So people interested in a seat or 2 seats, maybe a family wants 4 seats in the plane. So everybody has a size, and you have a knapsack constraint. You cannot just fit everyone. You have to choose a subset of people to fit. And of course, you would want to maximize social welfare in the sense you want to fit the people that have the highest value. So this is exactly a knapsack problem. But now remember the added difficulty that you don't know these values. So it's harder than the knapsack problem because you need to incentivize people to tell you what these values are. And both of these examples have this property that they're binary in the sense that you can either accept someone or reject them. You can either give them the service or give them no service. So an important distinction we're going to be making in this talk is about that. And an example which I know many of you have close to your heart is AdWord auctions, a third example where that is not true. So it's not binary. So you have advertisers on one side bidding for online search keywords. So their position, if you search for moving companies, there's slots, and there's a different click-through for a different slot. And each advertiser has a value for a click, essentially, right? So different positions in this case would give you a different click-through rate. So therefore, it's not like I either accept you and I give you what you want, or I reject you. Instead, I choose what level of service you're going to get. And that's kind of different than the previous 2 examples. And I'm going to come back to these. But before that, let me give you an overview of what we're going to cover in this talk. So I'm going to define these deferred acceptance auctions, which the benefit of these auctions are that they give rise to very practical and very simple mechanisms for the bidders. It's very easy for the bidders to participate, and they have impressive incentive properties. So in other words, they give very, very strong incentives to people to tell the truth, tell you what their value is, right? And even if you don't care about auctions or incentives, you can think of them as backward greedy algorithms. So this is essentially an algorithm that has this backward structure. I'm going to explain what this means. So even as an algorithm designer, at the end of the day, it boils down to solving an algorithmic question. Can I design a backward greedy algorithm that is efficient? An important limitation that these auctions had, the way that Milgram and Segal defined them, is that they only apply to these binary settings that I mentioned, the first 2 examples, either accept or reject. So the first half of the talk is going to be our first paper from EC 2014, where we essentially studied these binary settings and try to understand some fundamental examples. To what extent can we actually get social welfare approximation using these auctions? And the second half is a very recent extension so that actually we generalize this framework to settings where you don't have just binary outcomes. You can actually have multiple levels of service, and we also study what you can do within that. Make sense? Okay. So let's get back to the binary setting. So the first half of the talk is going to be about the binary setting. So remember again this single-minded bidders example. You have a set of bidders that want subset of items. You have to choose which subset to serve. And as I mentioned, this is an NP hard problem. So even if you knew the values, that's a hard problem to solve. It's even harder if you don't know the values and you somehow need to convince people to study them. And in fact, the way to think about this is called a non-single-minded combinatorial auction. You know these constraints. You know what subset of the participants you can satisfy at the same time, but you do not know what their values are, right? And what you can choose as an output is who wins, who actually gets what they wanted, who do you serve, and prices, payments. How much should they pay? And this is your tool to get the incentives, right? There's no other way. I mean, essentially, the payments allow you to convince people to tell you the truth. So you have to choose those payments, the combination of the allocation and the payments in a careful way, and prove that somehow the incentives are there so people shouldn't be lying. And the objectives are going to be to incentivize every person to report the truth, and we're going to approximately maximize efficiency in this sense. So which is standard in computer science in a worst case approximation sense. So we want the optimal social welfare to be no more than raw times the social welfare that our algorithm, our mechanism achieves, right? So we want raw to be as small as possible on any given instance. So we want to give this worst case guarantee. And those of you who are familiar with this, with auctions might think, oh, sure, VCG would actually do that. So we know that there exists this mechanism known as VCG, which actually maximizes the social welfare, so actually achieves raw equals 1 and gives you the right payments so that you get not only optimal social welfare, but also you get strategy proofness at the same time. People do not have a reason to unilaterally deviate in mind. But as I mentioned, if only you could solve this problem optimally, then you could apply this, but it's NP hard, so we cannot solve the underlying problem optimally, and therefore VCG is not applicable here. Because the moment you do not achieve the exact optimum, this whole thing breaks down. So the moment you have some error in your optimization, then VCG doesn't work anymore. And in fact, we're going to see there's other issues with VCG as well, but this is one important one. And in fact, this exact limitation that I'm describing here was the motivating reason that that gave rise to one of the first, actually, probably the first algorithmic mechanism design paper by Lehman, O'Callaghan, and Shoham in 2002, where they said, okay, let's look at the setting, single-minded bidders. Let's try to solve this, come up with a truthful mechanism. People should tell the truth. And we give an approximation of the optimal social welfare. And they suggested this simple greedy algorithm, where they're saying, just take the bids, ask everyone's value. So they report their values, and we order them based on this simple scoring function. Their value divided by the square root of the size of their bundle. In other words, the higher value you report, the better you look, the higher the score is for you. But the more things you ask for, the lower your score is. And this somehow summarizes the attractiveness of the bid and says, the higher this number is, you come earlier in this ordering. And what this mechanism says is just order the bids in this order, and then accept them greedily. Just accept the one with the highest score. That means some other people that have overlap with that have to be rejected. And then you keep going, but just accepting greedily based on that order, and reject the ones that are in conflict with things you've already accepted. And you charge everyone the threshold price. I'm not going to insist too much on prices. I'm going to be thinking about algorithms most of the time here, but for the sake of completeness, a threshold price is the minimum value that the agent could have reported and still survived until the end. So everyone who survives until the end pays the minimum value they could have reported and still survive. Yes, Costa.
Is it obvious to see what's so special about the square root here?
So it just works. It's not the case that everything else works. So if you just divide by the size, that will not work.
Is there a reason for that? Is there an intuitive reason why size would not be?
So I guess I haven't even defined, I guess, what I mean by works, and it's going to be an approximation guarantee, which is going to be the rest of the slide. So in particular, this forward greedy mechanism is strategy proof. That has nothing to do with the size. That was going to be the case anyway. So in fact, any monotone, any way that you score them based on increasing in the value, if you use threshold price, that would work. So that part does not depend on the size. But it also guarantees these approximation guarantees, meaning that the approximation factor of social welfare is big O of D, where D is the maximum bundle size. That's over all the bundles you have, what's the maximum size? That's D. Then you get a big O of D approximation with this. And you get a root M approximation, where M is the number of items. That first one, the D approximation, is definitely something you wouldn't achieve if you messed up with the root over there.
The second one? Is the second one achievable with?
So the second one is, I think, a bit more easier to get.
Okay.
What made this a fundamentally very interesting result is that, in fact, that's the best approximation you could hope for, even if you didn't have the private information part. Even if you knew everything, it's going to be hard to get better than this. Right? So in other words, that fundamental result by LOS, the Lehman-Shawn paper, said, you know what? This optimal approximation, the big O of D and the big O of root M, I can achieve it even if I don't know the values, right?
So was that best approximation ratio known before LOS? And if so,
no, it's there's hardness matching hardness results. So there's
that came later, or was it already?
Oh, you're saying that we can achieve the approximation somehow? No, I think that was already known that we can achieve that approximation.
And that was through a different algorithm? Or?
I believe so. Yeah, I believe it wasn't achieved by greedy I think.
This is a very simple algorithm.
Yeah, so this is a very simple algorithm that achieves the same approximation that you could ever hope for. So that was one of the fundamental papers in mechanism design, algorithmic mechanism design. And let's try, I think, just to make this, because although this is an old result, the first half of the talk, I thought I should go through this so you understand what deferred acceptance auctions are, so you maybe can appreciate the generalization that we recently came up with. Okay, so in order to explain this, let's look at a specific example. Let's verify that we understand what the forward greedy algorithm does. And let's say we have these 4 bidders over here. So there's 4 items, and each one of the bidders wants 2 items, right? A, B for this one, C, B, A, C, and B, D, right? So they want different items over there. And the question is, what would this mechanism we just saw do? Right, just to verify we agree on this. So all of them have the same size. So actually the denominator in this case doesn't matter. So it would essentially rank them by value and accept them in that order. It would first, therefore, accept this guy, CD, who has a value of 5. Therefore, once the mechanism accepts this, these 2 other ones have to be rejected. And then AB is also accepted. That's what the mechanism would do. And the prices, can you see what the prices would be, just to also verify this? What are the threshold prices? What is the minimum value this AB guy could have reported and still survived?
4.
Is it 4? So think about, what if he said 0? He would still survive, right? Because CD would still win first, and therefore, there's AB is just accepted because, CD was. And in fact, the same is true for CD. The minimum price CD could have reported and won is again 0. So he would have won anyway so one of them wins because of the other. And this is important part of the talk, in the sense that this is a property of many mechanisms. If you have this property, you use threshold prices, they would both win and pay 0. So although it's true that this is strategy proof, nobody wants to change their bid and lie. Can you see of a way where the 2 losers could coordinate and win? So if they said, okay, let's agree. So the 2 losers get together, they talk, and they say, is there a way we can actually beat the system?
Six and 0.
So 6, in fact, if they just say, so for the safety, so 6 and 0, I think one of them would have a high threshold price.
And then they will share that.
So they can just say, so because of the symmetry, if you think about it, if they both bid really high, so if we get together and say, you know what, just let's both bid infinity. Yeah. We will win, and for the exact same reason, we'll pay nothing for it. Right? So if these 2 guys get together and say, let's say they both bid 9. So they would win, pay nothing. So definitely there's strong incentive to form a coalition and lie this way. And this is a property not only forward greedy has, but also BCG would have. It would have the exact same outcome if you think about it. BCG would do the exact same thing, same prices here. So in important auction settings, you care about this too. There's strong incentives to deviate as a coalition. And the main theme of this paper is, what if we did this backwards? What if rather than a forward greedy algorithm, we did a backward greedy algorithm? Let's see what it would do then. So it would first reject. So rather than accepting greedily, it would reject greedily, right? So it would reject one of these two bidders. Let's say it rejects this one, BD, then reject this one. And then at the end, it accepts the remaining two, right? Because they're there. So it kind of backwards finds its way into the feasibility. So it rejects while things are not feasible, it keeps rejecting. So it would reject the least appealing people. So use that same scoring function. What would the threshold bids then? What would these guys have to pay for the CD and AB guy? What is the threshold price now?
1.
So yes, 1. So both of them have to pay 1. And in fact, what that paper by the deferred acceptance auction paper showed that if you do it that way, it's not only it's truthful, it's also group strategy proof. There's no coalition that can get together, deviate, and benefit. So it's much, much stronger. And it's kind of cute that if you just do that same thing, the forward thing backwards, that just works. Okay? So that's the whole focus of this talk, backward greedy algorithms. Because if you do it backwards, it's much better, but can you get efficiency that way? That's the trick. It's harder, in fact, to get efficiency that way. Okay, so now let me formally define what the set of deferred acceptance auctions is, so you can think about, what essentially as an algorithm. You don't care about prices. It just defines the prices. So it's a set of algorithms. Initially, everybody's active. So A sub 0 is N. All the people at stage 0 are active. And then it's a sequence of stages where while you cannot accept all the ones that are still active, A sub T. So at stage T, if it's infeasible to accept them all, what you do is reject the one with the lowest score, right? Just like we did before. So you reject the bidder who has the lowest score. And so therefore, in the next stage, you have one bidder less. And of course, everything depends on what is the score function. What can it depend on? So the only so this function, the scoring function, can depend on any information. It can change from round to round. It can be adaptive. It can depend on any public information. The only thing it cannot depend on is on the values of the other bidders. So for bidder I, at each round, I have a score, a number, that summarizes the attractiveness of that bidder. And this score can depend on any information, on what happened in the past, on who's still active, but not on the values of the people that are still active. It cannot in any way depend on this information. And as long as you do that, and at the end, pay threshold prices, doesn't matter. That there are prices, just think of that last thing, that there exist prices that make this group strategy proof and a bunch of other properties I'm going to discuss. So from an algorithmic perspective, the question is, here's a class of algorithms. What can you do with them, right? So you get to choose the scoring function we discussed before. Value divided by square root of size is clearly one of those, right? So it only depends for every bidder. His score depends only on his own value and on public information, the size of his bid. It can be much more complicated than that. But the important thing is my score cannot depend on other people's values. And at the end of the day, we summarize everyone's attractiveness into a score, rank them, reject the worst guy, move to the next stage. New scores. Reject the worst guy, next stage. And we keep doing that until we get a feasible subset. Does that make sense? So this is the class of algorithms that Milgram and Segal defined. And the question was, what can you do? But before we go there, let's verify also what are the nice properties you get if you manage to do that. So I said it has impressive incentive properties. So it uses, in computer science, you would interpret that as backward greedy algorithms, adaptive backward greedy algorithms, because they can change from round to round. And they guarantee incentive properties such that ascending clock auction implementation. Whatever you get, you can implement it as an ascending auction. Everybody sees a price that keeps going up from round to round, and they just at some point quit when the value, that price is higher than what they're willing to pay. So this is very, very important in many high-stakes auctions because you don't need to reveal, you don't really need to bid, report any private information. You just look at the price at the clock. When this clock is too high, you just say, okay, I'm out. Right, so this is a much more practical option.
One comment. So
yeah.
In the other definition, the definition you said that you can change the score from round to round.
Correct.
Score could go down or up.
The score is connected to the clock in a strange way. It's not the same thing, right? So the clock is your threshold price up to that point.
Yeah, but if you change your score downwards, also it won't go down.
Yeah, exactly. Okay. Because remember, your threshold price never drops. So if you survive a round, at every point, as you survive rounds, your threshold price might, if anything, increase. Right? So at any given point, your
no matter what happens to the score in the next round?
Yes. Yeah, because your threshold price was I had to survive that third round, even if I'm in the sixth round.
The threshold price is overall the
exactly.
round. Yeah.
So your clock is the threshold price.
Yeah,
correct. You get weak group strategy proofness. You actually get that there's no group of bidders that can collaborate and all benefit from that deviation. And you get a recent definition, obvious strategy proofness. I don't know if you've seen this. It's a recent definition by a Stanford economist again, where it says essentially even someone who cannot trust doesn't need to say, oh, VCG, yes, I did the math. It actually is truthful. I should say the truth. Even a naive person can actually see that it's better for them to tell the truth. So this is formally defined as obviously strategy proof. And finally, in some sense, it has privacy preservation in the sense that you don't really need to bid. You don't need to report any value. You just see the prices go up. And the winners, for instance, never reveal how much they value things. Maybe I had a huge value for something. No one needs to know about this. If I win, I won for whatever I paid. All they know is how much I paid. Okay, so these are very, very important properties that really motivate understanding these auctions better. And this is what they used in this $20 billion Spectrum auction that just took place last year. And these are properties that VCG and forward greedy do not possess in general. So therefore, this is the class of auctions that you would need to use. So what we studied in that first paper is, can we actually, get these nice, that's the obvious first question, right? We had this fundamental paper by Lehman, McCallum, and Shoham that actually managed to do that. Can we do that too using backward greedy algorithms? And the first thing the most natural thing I think to try first is that same scoring function, that value by this strange square root of the size that worked for the forward greedy. Let's try it out for the backward. And let's see an example of how it would perform. Let's consider this instance, right? So you have these items. So again, the vertices are the items. The edges are bids. Each edge is a different bidder. And the weights on the edges are the bidders. Okay, so this is an example, a specific instance. What would the forward greedy do? Let's remind ourselves this again. So it would accept this guy over here, right? First. Then that would mean it will have to reject this guy. Then accept this guy, reject this guy, accept this guy, reject this guy. So this is actually pretty good. If you look at this in this instance, it's actually the best you could ever hope to do. Let's see what it would do in the backward greedy. And you guess what it would do in the backward greedy? Exactly. So it would start by rejecting this one, and it would reject this one, it would reject this one, and so on. It would keep rejecting until it only accepts one thing. And you can imagine, I can make this path as long as I want. So it would fail miserably, right? And the main takeaway point here is that it's not even maximal if you do it backwards. So if you greedily accept, you know that at the end of the day, you definitely at least get a maximal solution. There's no more things you could add without creating some feasibility issue. When you go backwards, you're kind of trying to find your way into the feasibility region, but that might mean you rejected something at the beginning that at the end of the day, you didn't have to. So it's actually much more challenging algorithmically to get good approximations this way, which to me sounds exciting because we have this amazing incentive properties to try to understand, the reason to try to understand this class of auctions, and it's clearly algorithmically more challenging. So it kind of is a challenge from an algorithmic perspective. So in fact, this kind of a path example, we could fix it because if you look at it, one stupid thing that I did is I just said, I just look at the value and the square root of the size. Clearly the people on the ends are not causing as much conflict as the people in the middle. So people in the middle essentially are causing two conflicts. So you could somehow use the conflict number into your score function. Say something like, the higher the number of conflicts I have with other active bidders, the lower my score. So say something like value divided by the number of conflicts. And in fact, in this kind of example, this would fix things. So if you have just a path, if you do something like a value divided by, I think it was number of conflicts times conflicts plus 1, don't ask me why, but this is what works, this would actually fix this example. But it would only fix this one. So our first result is that there's no deferred acceptance auctions of the form value divided by size to any power times number of conflicts to any power that can achieve the desired approximations. So nothing in that simple form, even if we add conflicts, this is the family, a large family of scoring functions that one could try. We have bounds, lower bounds showing it would do worse. It wouldn't achieve those bounds. Make sense? So essentially, in order to achieve that same, if we ever hope to achieve these guarantees, we would need to come up with something different, something novel. And this is what we did. So the main result of that first paper, EC 2014 paper, starts from that initial hypergraph with these hyperedges and has this first scoring set of scoring functions which prunes the graph to extract paths out of it. And I'm not going to explain. I don't have enough time to explain about this. I'm happy to talk about this more later on if you want. But in somehow, we call it a locally highest bid mechanism. It just looks at the graph, the structure. It focuses on a specific item and only rejects locally. So to avoid this just rejecting in this arbitrary way all over the place, it focuses on an item, rejects locally, and then tentatively accepts whatever was achieved locally, and then extracts essentially a path out of the graph, and then moves on to the same thing, and extracts a sequence of paths. How do you actually implement this as a scoring function that is valid compared to that is in the deferred acceptance auction framework is not obvious. And then once you have that, then it's a path. Remember I told you that then you can do something with value divided by conflicts. Once you're here, that's easy. Once you've done this, you can actually get a feasible hypergraph without losing much more. And what we showed in that paper is that the first mechanism, the locally highest bid, actually achieves the D-approximation, and we can also get the root M. The reason you see tilde, there's under the root, there's also a log M that we had to face.
But not simultaneously.
So you can get so you can get with a log D also root log D, you can get it simultaneously with the same auction. But yeah, I guess essentially if you see, you can check if D is larger than root M.
Sure.
So I guess you can do it simultaneously. So you see the structure, you see how large D is. If it's more than root M, you pick your option.
Yeah,
so yeah, you can do it simultaneously. Okay, so essentially the message of this first half is that what we showed back then was that you can actually match the best possible guarantees, not only using strategy proof method, which is what Lehman, O'Callaghan, and Schramm did, but also using tricky backward auctions, backward greedy algorithms like the ones in deferred acceptance auctions. And the important thing is, although that sounds, I told you, oh, this is so strange, the scoring function does all these tricky things. Remember, that's all in the back end. In the front end, it's a simple ascending auction. So nobody needs to know how complicated, which is another thing I like about these class of auctions. It might be complicated in the back end, but no participant really needs to know what's happening in the back end. They just see clock prices. They're going up, at some point they quit. Right? So it's all this complication is under the hood. It's not affecting. Okay, so now moving on to the second half of the talk. So this was kind of restrictive, right? So as I mentioned, the AdWord auctions example doesn't fit into that framework. Everything I told you so far, I said, you start with a set of feasible things and you start rejecting. There's no kind of middle ground. It's not like, oh, you know what, I'll kind of accept you. It's reject. So everything they had defined doesn't apply more generally. It was kind of restricted to these settings where you have binary constraints. So the recent paper with Vasilis and Tim essentially tries to generalize the deferred acceptance auction framework so we can actually use it in much more general classes of auctions. And we define this generalized class of generalized deferred acceptance auctions, where just like before, we have a scoring function that doesn't change. It's exactly the same thing. We have a scoring function for every player that is adaptive, changes from round to round, and so on. The new thing is we add a clinching function. So we have this function GI, which at any given round tells you how much, if you were to be, we don't call it rejected anymore, we call it finalized. If you were to be finalized right now, G of I tells you what you should be getting, what level of service you've clinched already. Right? So essentially you start, you get 0 at the beginning, but as you stick around through the auction, this clinching function goes up and it says, oh, now if you were to be finalized now, you already got this item. Oh, now you got 2 items or 3 items or whatever the type of service is, right? So it gradually gets better and better. So when you finalize a bidder you finalize a bidder again with the lowest score, but he gets the level of service dictated by the clinching function. And that clinching function is also non-decreasing. So you cannot, by definition, you clinch the level of service means you're not going to lose it in the future. So you have that level of service. So it only gets better and better. And again, At any point when you clinch a level of service, you pay your threshold price at that point. So you survive up to this point, you clinch a level of service, that means that's how much your threshold at that point is what you pay for that level of service. So you get different prices for different levels of service. And importantly, we prove for each one of the properties I mentioned before that we maintain all of those properties. So our generalization works more in a much richer family of instances, and it has all these nice properties still there intact.
And this is still single-minded.
So single-minded is binary. So I'm saying let's go beyond that. Let's AdWords auctions think. So you don't have just.
But in terms of bidding, like
single parameter, you mean?
Single. What is it? A
single parameter.
Okay.
Yes. So we have in that paper I'm not going to mention, we have a multi-parameter setting in multi-unit auctions where you have multiple. You may have a decreasing marginals and so on. But yes. So the standard setting is just like in AdWords auctions, right? You have a value for a click. So your service, your level of service, then your value for different levels of service is implied by that parameter and combined with the click-through rate, say. Right? And I'm going to see also an example in scheduling. So later on. Okay, so the important thing to understand here is apart from the scoring function, now you have this clinching function, and what is going to be from an algorithmic perspective, again, if you don't care about the incentives at all, from an algorithmic perspective, what I found really exciting here is designing this clinching function means you can promise things. So if someone's finalized, they cannot get more than the clinching function. They get whatever they clinched. So in order to get good approximations, you try to promise, think of clinching functions as promises. You try to promise to people good levels of service early on, but at the same time, you better make sure this is feasible. You know, you're running against a wall. If you promise too much, then you might hit a wall. You might not be able. You better be feasible. So there's this additional constraint, which was not there before, that your promises have to maintain. It has to be feasible. Whatever you promise has to be feasible. And at the same time, you're kind of, as you promise things, you're restricting yourself in the flexibility. It kind of how can you divide up welfare later on? So let's make it a bit more concrete. Let's go to the AdWords setting to give you a specific example here. So in the AdWords setting, the thing that actually works here, we can actually get the optimal social welfare with all the additional guarantees. In fact, what we're going to show is that VCG is a deferred acceptance auction in this setting, in this specific setting. In fact, for those of you who know, for any polymatroid constraint, if you know what a polymatroid constraint is, this is just a special case of a polymatroid constraint. What we show is that for any polymatroid constraint, there exists a deferred acceptance auction that achieves the optimal social welfare. Okay, so let's stick to this example. So what I'm saying is, in this case, the scoring function is very simple, just your value. And your clinching function is the click-through rate of the slot as a function of how many people are still active. So initially, when there's, in this example, say we have these 3 bidders, initially there's 3 active bidders, so this A sub T has 3 people in it, so everybody's guaranteed nothing, 0 click-through rate, right? So at the beginning, I have nothing. So let's simulate this, right? So what would happen? So in the first round, so we start and we look at who has the lowest score. It's this bidder over here, right? So initially, as I said here, everybody has a clinching function of 0. So this guy has the lowest score. We finalize him, and therefore he gets click-through 0. He gets nothing. But then the moment he's finalized, A sub T becomes, it reduces by 1, and therefore everybody clinches 5% click-through rate, right? So the moment A sub T, the moment this guy is finalized, the set of active bidders shrinks by 1, therefore everybody else clinches 1 level of service. And then this guy is the next lowest bidder. He's finalized at 5. In other words, he gets that slot. And then the last guy clinches another level of service. And this is a toy example. This is a very easy example, as I told you. Even beyond this, in general polymatroid constraint settings, you can get optimal solutions this way. But just to verify what it means, what the clinching function means, that I can essentially define this function that changes over time and only increases. Okay, so let's see another example. Does that make sense? Any questions on this? So this is just verifying that what we did, in some sense, this is also kind of sanity check. We came up with this new framework. It better make sense in reasonable settings. So the previous framework, the first thing they verified is it works for matroids. Well, our multiple levels of service, we verify works for polymatroids. Right? So it's kind of a first sanity check that we actually have a good model.
One question. So what does the weak group strategy proofness mean here?
So it's that they cannot all strictly benefit
But suppose like bidder 2 and 3. Suppose they all reduce their bids by 10%.
So you can have some of them. So there's no external. I cannot pay you
transfers.
No external transfers. That's what it means.
But suppose they all reduce their bids by 10%, they all get cheaper, except for the last one, maybe. That's how.
There has to be some. I haven't thought about this example, but you know, there has to be someone who's not. So yeah, I guess for you, maybe the one relevant thing is this. Well, VCG, which is not generalized second price, but yeah, VCG in this setting is actually weight group strategy proof, and it can be implemented as an ascending auction. It's just a side result from what we get. That in fact, all these nice properties you get for VCG on any polymetric constraint. Okay. Now, for more interesting, which was the main result of the new, apart from the definition of the model itself, the real test was this. So we tried to solve, we thought, okay, how rich is this? Now we have multiple levels of service. How rich is the family of things we can describe this way? And we thought about scheduling. Let's try, this is a well-studied problem. Let's try to consider scheduling, right? So we have M identical machines. So let's say A, B, C, D, E, and F, these white columns are the machines. And each agent now owns a job. And of course, this is abstract. The machine could be actual server and actual job, but it could also be just tasks you're assigning to people or anything. And the job of each of agent's job, the size of agent I's job is P sub I. And the scheduler guarantees that all jobs will complete by some deadline D. Think of a kind of a cloud computing setting where I own these servers. I'm saying by the end of the day, you'll all be scheduled. But of course, different people have value for actually they care about their jobs. They'd rather have that complete earlier, right? So they're essentially, so every agent has a value VI for each minute or second or whatever of delay that he can avoid, right? So you guarantee that by the end of the day, you'll all be scheduled, but people have value for being scheduled at better. So in this case, by the way, the level of service is the completion time, right? How soon will your job complete? It can be the end of the day. It could be earlier. So the different levels of service are the different levels of different completion times I can guarantee for you. So if CI is the completion time of job I, our goal, which is a standard scheduling problem people have studied, is to minimize the social cost. In other words, the value, so the weighted completion time. So you want to minimize the weighted completion time. So this is like the social cost, right? So that if I reduce your completion time by 1, let's say 1 minute, then I reduce your cost by VI. So this is essentially saying I want to schedule things. I want to find the schedule, who goes where, in order to minimize the weighted completion time. And again, this is an NP-hard problem. Even if you knew everybody's values, if you wanted to minimize that objective, that's a hard problem. So the machines are identical. Jobs have a different time, but they have different processing times and they have different weights, right? So trying to solve this problem is actually NP-hard, even if you knew the information. So now we're asking, can we do it as a deferred acceptance auction? And the thing I want you to think about here is, what would this look like, right? So now you know the definition of a generalized deferred acceptance auction. We have this clinching function, which starts at essentially a low-level service, and I start promising things. Can you imagine what this would look like here? So essentially, the completion times I promise at the beginning. So I'm saying, I guarantee you will all complete by the end of the day. And then I start promising more, and as people are finalized, I start promising more and more, better properties, right? So I'm kind of scheduling people top to bottom, rather than many, if those of you who have seen scheduling algorithms, it's standard, the standard thing is, of course, start bottom up, start scheduling them, or in a centralized manner even. Okay, so let's say I think, yeah, so one thing, if you were doing it as an algorithm, one thing you might have thought about, like a list scheduling algorithm that's very well known for this problem, is the following simple greedy algorithm. Order the jobs based on non-increasing value over processing time. Again, those of you who have looked into scheduling, this is also known as the Smith ratio. So it's if everyone is the same value, then it's shortest job first, right? So you order jobs this way. And you schedule them in that order on the least busy machine at each step. In other words, let's say these are the processing times of the jobs that I have available. And let's say I've ordered them based on that. I'm not showing the weights, but let's say I've ordered them based on that order. So the way it would look, I would take job 1, assign it here. Job 2, assign it there. 3 here, 4, 5. Initially, it's obvious which one's the least busy. The tricky thing is now when I rise to 7, I look at the machine which is least busy. So this one's D, so I schedule it here, 8 here, 9 there, and so on. So this is a very simple list scheduling algorithm, and what we know about this is a very basic paper in this literature on machine scheduling. If you do it that way, you get a 1.2 approximation, right? So you can get this list processing algorithm and get yourself a 1.2 approximation algorithm. But again, now, this is bottom-up. This is scheduling people bottom-up. We have a much trickier task at hand. We want to start from the top and start scheduling backwards. And remember, I could say, oh, you know what? I promise everyone really good processing time. But I better make sure my promise is, I actually find the schedule at the end of the day where they actually get that completion time.
But before that, so if you take the forward algorithm, is it monotonic? Like, is it?
So if you pay threshold prices, yeah. So anything that's monotone in your value, the higher the value, the better then threshold prices should give you monotonicity.
So it gives truthful 1.2, but it doesn't give the weak.
Exactly. It has all the other issues. It doesn't give you an ascending. I mean, if you think of it, ascending auction, there's no way. How do you, for ascending auction, you have to start backwards. You have to improve. Like the longer you stick around, the higher more you pay. So essentially, what I'm going to define at the end of the day is going to be implementable as a clock auction. Everybody sees a price, and the longer they stick around, the better their completion times. But how do you do that? I mean, so I have a couple of minutes. So I want you to just go for this, because I spend a lot of time trying to prove this, and I think if I just show it, I mean, just the complication of it, that you want to start high up. All you know, in order to define the clinching function in the score, is everybody else's size. You do not know their value.
Just you have more than 2 minutes.
Okay. So you have everybody's size, but you don't know their value. Where do you start from? Where do you schedule the last guy? So let's say at the beginning, you're going to start with finalizing that first guy who has the lowest score. So let's say the score, I use that same thing. At the end of the day, I'm going to use something like that. But don't worry about the score as much as the clinching function. Where do I finalize that first person? How high? Essentially, what do I promise to everyone, right? So I want to make that promise only seeing the sum of the processing times, or the processing times of everyone that's not scheduled yet. So I know essentially, so it would look something like this, right? So at each stage T, a job I is finalized, and it is scheduled to CI, which is implied by the clinching function, right? So essentially, let's say the clinching function says something like that, and maybe this improves for others, and you start doing something like this, right? So you start scheduling people top up, and let's say you reach this point. So you've scheduled some people have not been scheduled yet. The question is, where does so you know how much space you have here left to schedule people. But then but the thing is, looking forward, the promise you're going to make has to not in any way depend on people's weights. So you cannot say, oh, what would the forward greedy algorithm do? I'll just do the same thing, because I don't know their weights. So I have to make a decision disregarding the weights of the people that come later on. Yeah, I mean, where would you start? So,
maybe the worst allocation among all the others.
So to make it feasible, you could always say, I don't know, like something huge.
You can always start at D, because you have a promise that it'll.
Right. No, I'm saying, let's say D is it's infinite. Let's say you have an infinite horizon. That's not really the constraint. Yeah. So the constraint is, if you start really late to make sure you have feasibility, then your approximation factor will be really bad. So if you start really late to make sure you're feasible, then your approximation will be good. Will suffer. So yeah, the question is how. So the first thing that comes to mind, at least for us, was you have to do something with a make span. Like if I were to sum the process, let's say I ideally packed everyone. I still haven't scheduled in here. How much height do they need? I better allow that much. That's kind of a lower bound. I better not pack them less. But also, they're not divisible. You cannot just move things across different machines. You have like chunks. There's a job that comes, so maybe the highest weight job actually is a huge one. So you have to make sure you leave space for that, because maybe it has infinite value and you don't schedule it first. You'll suffer immensely. So you better leave space for that guy to fit. So it's kind of that's what I kind of think this is a very novel type of optimization that you're trying to promise things, but also ensure feasibility. You have a constraint, you're packing things, but also you may want to make sure you get the approximation and the constraints at the same time. But anyway, so the thing that we eventually tried, so if the clinching function is, if the completion times that I allow is too large, then I get a bad approximation. If it's too small, then I might end up with an infeasible schedule. And the important thing is it cannot in any way depend on the values of the people that I have in schedule. So I guess I took enough time trying to let you think about this. The thing we actually did is we're saying let M sub t be the fractional makespan of the people that have not been scheduled yet. So this is the set of people that have not been scheduled yet. If I sum up the processing times and divide by the number of machines, this is kind of the lower bound. There's no way I can get better than that. So even if I were to optimally pack everyone else, that's the best completion time I could ever guarantee for the last guy. And PT bar is the maximum processing time among the people that have not scheduled yet. So overall, because there's also, as I mentioned, it's not fractional. If there's some huge guy over there, I cannot really promise. Somehow it will change what I can do. So what we said, the goal that we set, where we finalize people, is the fractional makespan plus 2 times that maximum processing time. So saying, let's start with this minimum thing and give it some leeway of 2 maximum processing times, and let's start from that. So that part, and it doesn't matter. So, and essentially, by the way, because you start packing things, you might not be able to actually get your goal because maybe it's higher than what is. So it might not be feasible to schedule something up there, but you just make it as late as possible up to that point. And let me make it more precise. Oh, and the way it would look like, so you start there, you schedule the first guy, based on his processing time. Since this guy was scheduled, it reduces M sub t, for sure, by his processing time divided by M, so that drops. In fact, if he's the guy with the maximum size, that might drop too, right? But this always drops, and then you schedule someone else, and you keep going like that. You keep scheduling people. So the tricky thing, though, is that you might leave some open space here, right? So you start packing, and it's not clear why. Now maybe there's inefficiency because you didn't pack everything there. Something sticking out from below, right? So it's not like everything here is always free. So it's not obvious that this would work either. But yeah, so I don't have enough time to prove these things, but it works, and I'm going to talk about the approximation. Feasibility was what took us a lot of time to prove. It wasn't obvious that this will not keep going too fast, too low for us to be able to pack everything. And in fact, this is tight in some sense. Let me show you in what sense this is tight. Let's say I start with this set of examples, right? So I have these processing times. So the first thing my score would tell me to finalize is 100 seconds. Then it's 50, 100, 75, 100, 87.5, 100, and so on, right? So let's say we start from here. When I schedule the job that has size 100, then this drops by how much? By 100 divided by 2, right? Because I have just 2 machines. So it drops to this, right? 100 divided by 2. That's how much my makespan, my fractional makespan drops. And then I schedule the next guy who was exactly 50, so he's packed over there. And now my next job, so it drops again by half. So always it drops by half of whatever I schedule, right? Because this PT bar will not change throughout. And then I schedule this, it drops by half. And you will notice that this keeps lagging, right? The red line keeps staying further and further back, and I'm still packing things here. And eventually, you see that it's always kind of getting closer and closer to the limit of what I can pack. And this, in fact, we can show that in the limit, if you were to say you have alpha times MT plus beta times 2 PT. If you did alpha and beta anything less than 1, so if you decrease them, then it will be infeasible. So it's exactly tied in that combination, in that sense. And also, and the result that we get is this. So the algorithm, the actual algorithm that we have is at each stage, if there exists a job so we have to make that tricky decision here. If there exists a job whose processing time is greater than half the makespan, then we have to do something else. Then we finalize the job with the largest size. Otherwise, we just use that scoring function. And we schedule the finalist job so that it's CIT, so what I mentioned before, as large as possible, but no more than their goal that I set. And we prove this approximation. So we actually get, so unlike some of the previous results that I showed, this actually gives you a small constant factor approximation for an NP-hard problem using this class of auctions. The way to think about it, really what it does is we manage to prove that our scheduling, and this is why we need this trick over here, the first if. Whatever the forward greedy algorithm does, we make sure that point-wise, every job is not delayed by more than a factor of 4. So whatever forward does, we do no worse than 4 times that. So how you can guarantee backwards that, because you don't know what position this guy would have been in the forward, you don't know what the structure of the forward would have been, but somehow we managed to show that no job is going to be more than 4 times away. So this is exactly 4 times that initial approximation that I showed you, the forward greedy. So we lose a factor of 4. Okay, and this is my last slide. So to summarize, apart from the first part where I talked about the single-minded, and there's a bunch of results I didn't show about the limitations that you cannot get more than a logarithmic and so on. There's a lot of results in both papers I didn't mention. So some of the results in this more recent one that I didn't mention. So I mentioned the polymetric constraints and the job scheduling. I didn't mention that we also consider multiple knapsack constraints, and we get a logarithmic, which in fact is optimal. We also consider, back to Arniak's question about single parameter. So most of our results are single parameter, but we also consider multi-unit auctions in that latest paper. And we define a generalization toward that too, which essentially treats each marginal as a different bidder somehow. That's the way to think about it. So each marginal that you report, we treat it as a different person, and we get a 4 log n approximation. We don't know if this is tight. So this is one of the main open problems, understanding whether, but it's kind of, we try to get lower bounds, but imagine getting lower bounds for which one of the properties. Maybe for weak group strategy proofness, say you cannot do better than log. It's kind of hard to argue, like we tried lower bounds for group strategy proofness, but it was not easy how to get there. But yeah, we have that positive result. We're thinking about whether we can actually improve it. And there's several open directions. What I really like about this setting is that it's so new that not that many people have managed. There's a lot of low-hanging fruit. For instance, there's many interesting special classes of single-minded bidders. We just said worst-case single-minded. A special case would be interval bidders. Let's say you just want to, so if you want to schedule a job and you want from, 2 to 4, you want the server, right? That's again single-minded. You can think of seconds as items and you're a single-minded bidder, but it's not like an arbitrary structure. It's not an arbitrarily single-minded constraint. It's like interval bidders. And for that one, for instance, we can improve upon that. But there's different other constraints you can consider, and both in the binary and in the multi-parameter settings. So these are just the first problems that came to mind. And even more generally, we have not used priors. All of our results are in a worst case. So if you know a distribution about the values, you could do much better. And this is public information, but there's no deferred acceptance auctions that use priors. And finally, one that I'm actively working on is all of the statements that we have is about deterministic mechanisms. If you allow randomization, it's not clear. You can actually potentially do much better than that. So randomization is not part. So the one obvious thing is just randomize and decide what auction to use. So that clearly won't affect the incentive properties. But a trickier thing and a more compelling thing would be to randomize seeing the value. So as you go, somehow bake into the scoring function some randomization. It's not obvious what can this randomization depend on without breaking the property. So generalizing the framework to include randomization is, I think, a very important direction to consider. And that's it. Thank you very much.
So one question is in the spectrum auction, where they first defined this deferred acceptance.
Yeah.
So it has all the good properties, but did they also look at what score function would give good efficiency? So
the interesting thing is that they actually, which I think, so in the real setting, they had some special cases. They couldn't, I don't think they used exactly, they approximate the incentive properties. I don't think they used it as a guideline, but they didn't exactly get all these nice properties. But it's funny, they actually use a square root somewhere in the scoring function. It's like, in that sense, you have those constraints over, if a broadcaster is in a specific city, you cannot assign the same frequency to a broadcaster that is in the same kind of vicinity, right? Yeah. So really what they're doing is they're trying to buy off some of the frequencies, making sure that whatever's left, they can redistribute and pack. So the constraints are kind of these kinds of constraints that you cannot have two broadcasters in the same And they're using, I think, something like value divided by number of kind of conflicts like that as square root. And I asked why, and they said, well, that's, there was that paper, so there was some justification. Because the interesting thing, unlike what we're doing here, is we're saying, let's design an auction of, we just choose which one it is. In that setting, there's a game even before you get the auction. In deciding what auction we're going to use. So some people want this auction, the other people like that auction, right? So as a mobile provider, I might actually prefer one auction to the other. So they're kind of lobbying to decide which one of the auctions to use.
Okay.
And therefore just saying, you know what, there's a paper that uses square root, we'll just go with that, is kind of, I think, just solve their problems in the sense that they could just say, we're not accepting anyone's.
Sure. But if you look at that, there's some graph problem there, right?
Yeah.
Some allocation problem, some conflicts and so on.
Yeah.
You could do similar math to figure out what's the best score.
Yeah.
Once done that.
I think so in reality, because these are worst case approximation guarantees, in reality they said that they kept getting in all the simulations, they got 99% approximation. So they said, the actual instances that they got, it actually seemed greedy. In fact, so Paul Milgram, so when I presented this in their seminar, so one thing he asked was, he was really interested in this greedy-like things. Why do they work? How do you parameterize how close to a matroid you are? Because for matroids, greedy works. So he was really interested in finding approximations to the matroid structure that might explain why did this work in our case. There must be some structure that allows it to work. What is it that works? But there is something in the real graph that actually makes it much easier than worst case examples.
Okay.
Yeah.
So in your single-minded case, is it truthful against lying about this set? Like if I say a bigger set?
No, so as I mentioned, the whole thing is single parameter. So the way they define it was not only binary, it was single parameter, meaning your only private value is your value, your bid. Your set is not private. So that's another generalization. As I mentioned, the only multi-parameter thing that exists for deferred acceptance auctions is this last thing over here. So what you're saying is essentially a two-parameter setting where you report your value and your size. We have no idea. I know the things we already have do not work. So, and you're right that actually Lemon O'Callaghan Shohan paper actually works even for that. So that forward greedy works even if your bundle is private. But yeah, so that's another open question. We proposed that at the end of the first paper, could we design something? But you need a different framework to prove that you still don't get group strategy proof issues. Right? So you need to prove that there's a way to use these two parameters without creating any issues. Or either that or just come up with a specific auction and say, I don't know about a framework, but this one actually happens to work. But there's no known. Good point. Yeah, awesome.
So I don't know if this was the first ever approximation algorithm for scheduling with idle times. But
with idle, oh yeah.
So the question is, this introduces some concept of envy freeness, in that if I'm able to observe the outcome, I envy what I could have gotten, because the processors have idle times. So if you ask to get envy freeness as well, this sort of, is it too much to ask, or if you just collapse the schedule, do you get it, or does it?
So you're saying that people, because essentially they weren't willing to pay that price, that means they don't envy each other. That's why you're saying envy freeness in that sense with the price included. So
yeah, like you're keeping your processor size.
So you're saying if I relaxed, so if I knew the values and just if I knew everything, could I achieve envy freeness in a more efficient way? I guess is that the question?
Yes.
I imagine that.
I mean, even in this setting, right? Suppose you collapse your scheduling.
Yeah, whether that gives you an envy-free, what would the prices be though? Right, so there's also prices that you need to address.
Yeah, so if you keep the prices.
If you keep the prices, I guess everyone's still happy, meaning they pay less than they, but it's not obvious that, it's not obvious at all that this would still be true. But yeah, when it comes to delays, I mean, people have looked at delays, I guess, in coordination mechanism settings, right? So when you want to create incentives when people can choose what machine they'll be scheduled on. And although I guess it seems somewhat unappealing to introduce delays at first sight, you can always just use those times to do something else, right? This is just saying I have a set of bidders I need to satisfy. It's not like this is the only thing you're doing with your servers. You can also have, you know what, during this idle time, I'll just run my own processes or something. So yeah, it kind of just addresses the incentives for a specific group of people, as long as there's no kind of contamination between the people you're addressing and what you're going to do with the idle time, then that should be fine. Cool, thanks.
Thanks again, Vasilis.